Hello, I am Joseph Taylor, and this is going to be my homework too. I'm going to lump parts A and B together here, since that'll just make it a little bit easier than making an entire other video for 2 minutes of work. But as you can see, I have the problem drawn up here, but you can't see it very well, which I realized after my first videos. So I went ahead and wrote it right there. So as you can see, we have our tank with 3 streams going in. One of the streams, and well, all their respective quantities are right there. But the exit hole is going to be 0.1 meters squared, and the entrance, the cross-sectional area is going to be 1 meter squared. So these streams respectively are 80 degrees, 65 degrees, and 90 degrees Celsius with a concentration of 0, 1, and 5. And then the flow rate for number 1 is going to be 0.5 cubic meters per second. For 2, it's going to be 0.3 cubic meters per second. And for 3, it's going to be 0.6 cubic meters per second. So, as you can see there. So now the first thing we're going to do is we have to find 3 different differential equations. We have to find one with respect to volume, we have to find one with respect to height, and we have to find one with respect to temperature. So I'm going to start off with the one with respect to height. And to do that, we can go ahead and do a mass balance. So that's going to be dV dt is equal to Q1 plus Q2 plus Q3 minus Q out, as we can see here. That can be then simplified if we do volume as the cross-sectional area times the height, and then we can go ahead and make Q1, Q2, and Q3 a summation and just call it Qn for this first circumstance. So then from there we will get, and then, yeah, here, I'll just write it out. AC times dH dt is equal to Q in minus Q out, as we can see there. Good, maybe. There we go. But then from there, we can simplify Q out as the cross-sectional area of the hole times the square root of 2GH, which will then look like that. And then from there, we can go ahead and plug that in, and then we will get AC times DH dt equals Q in minus AH times the square root of 2GH. So then that will look like that. And then from there, we can divide over the cross-sectional area. So then dH dt is equal to Qn minus AH times the square root 2GH, all over the cross-sectional area. And that is going to be our first differential equation. Right there. All right, so I will go ahead and tear that page out. So now the next thing we are going to do is the change in concentration. So we can start by doing the same kind of thing with the volume over T, but then this time we're going to multiply it by concentration. And then that's going to be the summation of the concentrations times their flow rates minus the flow rate times concentration. So we can go ahead and write that. So it's going to be Q1 CA1 plus Q2 CA2 plus Q3 times CA3 minus Q out times CA. And since this is a mixed batch reactor that we are saying is perfectly mixed, we can go ahead and say that the CA is just CA. So it's just the concentration. And then we end up with this equation. Now, from there, we can go ahead and do the same type of thing we did before, where we take the volume and we separate it into height times area. So then we can do the AC times DHCA over DT is equal to, and I'm just going to go ahead and make this a sum of the Q's and the concentrations. And then minus, and I'm going to go ahead and substitute the Q out for the same Q out we used before, the AH times the square root of 2GH. All right. And then that'll leave us with this equation right here, this second one. So then from there, we can go ahead and divide over the AC, or the cross-sectional area of the entire tank. And then that's going to give us DHCA over DT is equal to the sum of the flow rates times the concentrations going in minus the cross-sectional area of the hole leaving times the square root 2GH times CA over the cross-sectional area of the hole, which will then give us this equation. And then from there, we need to separate this out into its individual parts to get the concentration by itself. So to do that, we're going to do the product rule. And so we are going to do the concentration times dHdt plus the height times dCA over dt. And then we're just going to set that equal to the previous equation that I had just shown you. So that's going to be the summation flow rates times concentration minus flow rate out, which we separated into the AH times the square root of 2GH. And then that's going to be times the concentration out all over cross-sectional area of the tank. And then from there, so then we will end up with this right here. And then from there, we can go ahead and just simplify out. And once we do that, we get dCA over dt is equal to 1 over the cross-sectional area multiplied by the summation of the flow rates in times the concentration of the flow rates in minus the AH square root 2GH CA. And then that's going to be minus CA dH dt. That looks correct to me. So then this is the final equation we're left with. And once I have all three of these, I'll put them up on the board so that they are a little more clear. So now the last one to do is the temperature here. And to start out, we can't do this one the same way using the volume since the temperature is not in respect to the volume. So what we're going to do is go ahead and mash it all up. So it's going to start with the concentrate or the cross-sectional area multiplied by dH rho, and then the specific heat capacity times the temperature all over dt. And then that is going to be equal to the summation of the flow rates in times the specific heat capacity times rho times T in, and then minus Q out. And in this case, I will just leave it as Q out because once we put it into the code, we can put Q out is equal to the square root of 2GH times the area of the hole. So then I'm just going to leave it like that, and then rho times the specific heat times the temperature. And then we are left with this equation, which is a big jumble. But we're going to do the same thing again, where we are going to divide over the cross-sectional area and then use the product rule. But first, what we can see here is that we have some canceling out to do. So we can cancel out the specific heat. See if I can write. Cancel that out. And then that cancels out here and here. So then from there, we can go ahead and do what I just said, transfer the cross-sectional area over, and then use the product rule. So I'll go ahead and write that out. And so that's going to be T times dH dt plus H times B big T d little t. And then that's just going to be summation of the flow rates in times the temperature going in minus the flow rate out times T. And I'm just going to leave it as T just for the same reason I left the other one as the regular concentration, because it's a uniform reactor, so we can assume that the temperature coming out is constant. So then from there, we are left with this right here. And then we can continue on doing the same exact thing where we just basically simplify it out to find our actual equation. So what we're going to do is, oh, I forgot to add the AC, the cross-sectional area. There we go. So this is our current equation before simplification. And all we have to do to simplify now is move over the dH dt times the temperature, and then we will be left with our equation. So let's go ahead and do that. So we're going to be left with d big T over d little t is equal to the summation of Q ins, so all the flow rates in, times their respective temperatures, minus Q out times T, all over the cross-sectional area. And then we are left with minus dH dt all over H. Looks right to me. So right there. All right. And then I will go ahead and write these up on board. dH dt there's down. And then for concentration, it's going to be 1 over AC times the summation of the flow rates in times their respective concentrations, minus cross-sectional area of the whole times the square root 2dH, which is just the flow rate out. And then that's going to be multiplied by CA, and then minus CA dH dt. And then our last one, which is the temperature, going to be 1 over H times UN times T and minus Q out times T, all over the cross-sectional area minus dH dt. All right. Just so you can see a little bit better, I'll go ahead and take you on a tour just to see the equations. All right. And then from there, we can go ahead and get to coding. Alrighty. Now we're jumping into the coding portion. I did notice at the end of my previous video that there were several papers on my desk, and I just wanted to show you what they were so you didn't think I was cheating. These are just the notes that I was actually writing during the video. And then the other two sheets you saw were from a different class. I'm not sure if you can see, but leftovers from finals week. So I apologize for that. So I'm just going to go ahead and get into coding. First, I'm going to go ahead. I've already written in the imports, and I've already written in the subplot making portion because syntax is my kryptonite, and that would have taken me 20 minutes. So anyway, we'll go ahead and get into it. So for gravity, that's going to be 9.81. And then next is going to be the concentration. Or no, that's the cross-sectional area. And then that is going to be 1. And then next is going to be the area of the hole, which is going to be 0.1 squared. All right, and now let's go ahead and do the T end, which we'll just put as 100 seconds, because that'll be a long time. And then T in, so these are going to be the initial temperatures. And then that's going to be an array, which I believe is NP array. And then for an array. And again, this is just the problem statement that I wrote down for the derivation portion of the video. So for the initial temperatures, we have 80, 65, and 90. And then we have the CA in not. So these are the initial concentrations. Just going to be another array. And those are 0, 1, and 0.5. And then next is going to be our Q values. And then that is going to be 0. That is going to be 0.5, 0.3, and 0.6. All right. Now, I believe that's it. So now this will be for part B, what I'm plugging in here. So I might switch tabs here. I don't have it open. Oh, there you go. So we're going to do T in 2 is equal to T in not copy. And then, well, first, actually, let's go ahead and run these and make sure they work. Perfect. Okay, great. And then CA in 2 equals CA in not dot copy. And then for the last one, since this is what changes in part B, this is going to be another array. So it's going to be np dot array. And then those numbers are 0.55, 0.28, and 0.8, 0.6. I typed in and. Okay. So now, next, let's go ahead and do, let's go ahead and define the right-hand side. Please ignore my dog barking. Alrighty, so those are our inputs. Or not complete. Actually, yes, those are the inputs. So I'm gonna have to edit out all the cursing. I apologize. So now we have Q out. Which is just going to be set equal to what we did before, which is the area of the hole times, so we have AH times the quantity 2 times G times H, and then that is going to be to the half power. And then next we're going to have DH dt, which is going to be equal to and to do a sum, we're going to do np dot sum of q in minus q out divided by AC. And then for dCA dt, we're going to do same thing, np dot sum of, except this is going to be the q in times their respective concentrations minus q out times CA minus Sorry, I was cursed again. CA times DH, 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 DT, or DH, and then divided by D, T, small t. Or wait, no, it's just H. I'm stupid. Don't know how it gets home from that. But anyway, now we're going to do DT, or D big T, D little t, which is going to be equal to NP dot sum Q UN times TN minus Q out times T. Forget if I put a big T or a little t. I put a big T. Okay. Okay, all those variables look right. Okay. Times T, and then that is times DHDT. All right, and then divided by H. Puts home every time. Return NP dot array, because we wanted to make a different plot for each of those. Let me double check my equations. Those look correct. And we wanted to return an array because we want there to be 3 graphs, one for each of our things we're tracking. So the concentration, height, and temperature. So then we're going to do NP dot array, and then do that maneuver, and then DH, DT, DCA, DT, and then T, DT. All right. Let's run, make sure everything works. Perfect. Alrighty, and then next we can start with the solution. So we're going to do sol equals root lambda, yep, lambda right hand side. All the variables then. So then we're going to have Q and not, Q and not, CA in not, and then T in not, and then just like no. Okay, yeah, there we go. And then we have np dot array np dot sum Qn not H squared divided by 2 divided by G, and then 0, 5, and then 70. I believe let's try this. UN not is not. Oh, need to make sure I'm doing my spaces and or my capitals and lower cases right. Hmm. V is not. Hmm. I'm going to pause the recording for a second. Alrighty, so we're back, and after about 10 minutes of looking at it, I couldn't figure it out. It's saying unsupported operand type, and I have no freaking clue what that means. So we'll just push forward, and hopefully I got enough of it right. So of IVP, lambda, T, B, right hand side. Two, two, two. And then from there, we can do it from 0 to end. And then X method. For the method, I'm going to use rad down, I believe is the right name for it. And then for sense output, equals true. And then I already have that. T end is not defined. spelled it wrong. I'm sorry, the code I have that is written exactly the same way worked, and this is not, and I don't know why. Explain error. This makes no sense. So this one's saying, let's check all. I'm sorry, I really have no clue what's wrong. I'll try to get it to work, but if I can't get it to work, this will probably be what I end up submitting. Thank you.